As you may or may not know, there are 4 fundamental kinematic equations, and in this video I'd like to go over how to derive each of them. So an important assumption to note before I start is that all of these have constant acceleration. None of these equations work if there's variable acceleration, which is why the quantity of average acceleration will be used to start. So from my last video you'll know that the average acceleration is equal to the change in velocity over the change in time, which is also equal to the final velocity minus the initial velocity divided by the final time minus the initial time. But the initial time is usually 0 because they'll give you a question that says find the time when such and such happens. You won't be given an initial time in most questions. So for convenience's sake, we can substitute ti for 0 and say that the acceleration is equal to a change in velocity per unit time. So now, simply taking this time term and putting it on this side gives us Vf, or the final velocity minus the initial velocity, will be equal to acceleration times time. So now bringing the initial velocity over here gives us the final velocity will equal the initial velocity plus acceleration times time. And this is, in fact, the first of our 4 kinematic equations. And I'd like to represent this graphically. Say we had something that looked like this, with time on the x-axis and velocity on the y-axis. So there is a intercept here. This is vi, or some textbooks notate it v0, but it's really the same. And it'll be a linear relationship because the acceleration is constant. So as you can see here, we can divide the area under the graph into 2 sections. This distance here can be represented by vi, and this distance here will be represented by a t. So the reason that the graph goes upward is because t is constantly increasing. The acceleration, as I mentioned before, will always be constant. So in order to derive future kinematic equations, it's also important to note that the average velocity can be represented as a sum of 2 velocities divided by 2. And if you're familiar at all with how to calculate an average, you'll know that you can add 2 quantities together and divide them by 2. For example, if let's see, if I have the numbers 3, 6, and 8, the average of these 3 will be 3 plus 6 plus 8 divided by 3, which is 17/3. Ooh. Okay, so the average velocity can be calculated by taking an average of known velocities. That makes sense. So if we substitute this into an equation that we're already familiar with, the average velocity should be equal to the change in displacement divided by the change in time. We should be able to calculate a change in displacement as equal to the average velocity times the change in time. All I did was take this term to this side and substituting this into this. And when I say v, I really mean the final velocity, but since that's usually given, you can leave out the f. So this will be equal to vi plus v divided by 2 times t. And this is, in fact, our second kinematic equation. And I'd like to explain 2 things that I did here. The first is I put the brackets on delta as optional. In some questions you will not be given an initial displacement. But if you are, then you could rewrite this as the final displacement minus the initial displacement should equal vi plus vf over 2 times time. The other thing that I did is I took away the delta from time. And that's for the same reason that I took it away up here. Rarely are you given a question where some time has already transpired before some motion of interest has occurred. So give me a minute to erase. I'm going to go over the last 2 kinematic equations. Alright, so these are the two equations that we've found so far. But to find a third, what we can do is we can substitute this equation, equation number 1, into equation number 2. So let's try it. Equation number 2 can be written as 1/2 v0 plus v times time. So let's substitute this v for v0 plus at and see what happens. The displacement will be equal to 1/2 v0 plus v0 plus at, the whole thing times time. Let's cancel a few terms. 1/2 of 2v0 plus at times time. And then now expanding the 1/2 and the time gives us that the displacement, or d as they call it in some books, should be equal to v0 times time plus 1/2 at squared. And this is equation number 3. That says that the displacement of any object with constant acceleration, and you'll see a lot of these in questions where some object is falling, like if I just drop that, the displacement that the marker has traveled can be calculated by taking 1/2 of the acceleration that it had, which in the case of gravity is 9.8, times the square of the time that it took to reach the ground, and that's how far it fell. And in some cases you'll see that there will be an initial velocity, but in a lot of questions they do not have that, so sometimes you can omit it. And omitted, it looks like this. The distance is 1/2 at squared, and this probably looks familiar to you.